Okay, so I think I found I found the best setup finally. I managed to do split screen. No, I managed to split screen. So on my right is gonna be voice. Hello, how are we doing? Hello. Hello, how are we doing, Rex?
Hey, we're doing great. I'm caffeinated and crisis free, so fire.
Just drinking a coffee as well. Anyway, look, let's go. So I'm gonna have you on the side. I'm gonna maybe look one question. So I'm trying to solve these. Let's do these. Let's do these. Let me think about one thing. Uh,
Sound
no, actually, you know what? Because you're too impatient and you talk too much. I'm gonna put you in pause for a sec. I'm gonna basically stop the conversation and come back in a second. Okay, whenever I need you.
okay.
All right, we're gonna do no. We're actually. I'm not gonna use Simpai. Um, hey Rex, is Simpai good at doing computations with group theory? Hey Rex, is Simpai a good package to do group theory computations?
Yeah, SymPy's solid for group theory. It's got tools like permutation groups, finitely presented groups, and even polycyclic stuff baked in. Think symmetric, cyclic, dihedron, all computable without sweating the details. If you're just dipping toes, it's way friendlier than rolling your own. But watch out, it can chug on huge groups. Want me to walk through a quick example?
I want to know like what type of like for example, does it have support to compute, let's say, I don't know, the representations of a group over a field?
Yeah, SymPy.
Yes. Hello. Hey Rex, you there?
Yep.
Can SymPy calculate can SymPy calculate representations of a group over a field?
SymPy can handle character tables for finite groups, like irreducible representations over complex numbers, using the SymPy combinatorics.group constructs character table or SymPy combinatorics named groups stuff. For actual matrix reps over any field, though, it's spotty. You'll get basic ones for symmetric or cyclic groups, but fancy finite fields or big reps might need tweaks or jumping to sage math instead. Want specifics like S3 reps over GF2?
Can it do it with, like, let's say I define a generic field that I only know that it has characteristic 2, for example, and that is large enough to have like a group act on it?
SymPy's field game is, let's say, not championship level. You can set up finite fields with characteristic 2, like GF2n, via SymPy.poly's domains, but defining a char2 field that's big enough for group actions, that's a stretch. SymPy doesn't really do abstract, unspecified large fields.
That's
It
what I
likes
thought.
concrete ones.
That's
For
what
group
I
rep,
thought. That's what I thought. But maybe we can do a concrete one. Can you give me a big field with characteristic 2 in SymPy as an example?
sure, easy one. Let's whip up GF256, which is GF2 to the 8, big enough for most group action fun. In SymPy, you do from SymPy.poly's domains import GF. From SymPy.poly's domains, honestly, just grab the base field, like R is GF28A. Boom, your char2 playground. Then reps could live there if you're building matrices by hand, like permuting basis vectors. Not automatic, but doable. Want code for, say, Klein 4 group acting on it?
Yeah. Yeah?
Cool. Klein 4 groups perfect. Abelian. Small. Reps are chill. Picture this. GF256 as your vector space, say 8-dimensional over GF2. In SymPy, you'd set R is GF28, A and 0. Then build the rep matrices manually, like diagonal ones since it's abelian. Eigenvalues in the field. Want me to sketch the code? Group acts by swapping coordinates or something. Tiny example. 2 generators swapping first 4 basis vectors. I can write it if you're caffeinated enough.
No, thanks. I think I'm like, I don't feel that's the right approach for what I want to do. I'm gonna try something else on your text chat. So stay there for a while. I'll come back to you if I need you.
Got it.
Oh, maybe wait. Maybe don't go. Like, can you explain me what is Sage Math and how does it work and what the features are for group theory stuff?
SageMath? Oh man, it's like a Swiss Army knife for math geeks. Open source, built on tons of packages, like GAP for group theory, Maxima for symbols, and more. Think Python with superpowers. You script in it, install free, run locally or cloud. For group theory, goldmine. You get permutation groups, abelian ones, even infinite character tables, homomorphisms, reps over fields like GF28. Way beefier than SymPy. Handles S3 over finite fields without breaking a sweat, using stuff like permutation group morphism or matrix group. Want reps? Define matrices in a field. Let it crunch conjugacy classes or orbits. It's not just compute, it's interactive, so you tweak and see. Better for your char2 wild ride. Curious about a demo?
Can it do infinite fields?
SageMath handles infinite fields fine, like rationals, QQ, or reals, RR, since it's basically Python with GAP under the hood. You define them quick. F equals QQ.x for rational functions, or even algebraic closures if you're nuts. Group reps over infinite fields? Totally. Say SL2, QQ, or whatever monster, and it'll compute irreps, units, lattices, no problem. Just more memory hungry if your group's wild. What's your angle? Infinite char2 or just infinity in general?
No, I'm gonna try one thing. I'm gonna try to specify a problem that I have in SageMath, and then see if I can get it to work. Thank you. Given this problem, this description. Give me SageMath code that specs S, D, and D R times S. Okay, so what is it doing? Symmetric group D, and then it's doing So that's one thing, but I keep trying to use tools, but like maybe it would be able to just reason through these by itself. But okay, we have these, and then we have that. Can you add? Can you add to the script the definition of k be a large enough field equals to 2? Can it do these? Where is k defined? K. Oh, these. I mean, kind of. Kind of. It just does a specific example. What's GF? Galois field. Okay. Can you now calculate representations of G over K in the script? Since the code is K. Define K, construct G, cart a table of it, or attempt to construct matrix representations of GF. So I built a function actually, get representations. How do I install Sage Math? It's a binary release, but is Sage Math like tour quick start? Okay. So it doesn't really work in the console? The hashes. example, try this. It's downloading it. Okay. So what it's doing is trivial representations. It's hard coding the trivial rep, and then it tends to construct other result representations. Since just often we need representation over. To the representation. Still pretty much actually just goes and tries to do this by hand. Like it doesn't seem like there's a way to compute these. So maybe I might as well just try to reason my way through it. You know what I mean? By basically telling the model, hey Grok, hey, you are an amazing group theory mathematician. Can you help me build up a solution to a problem? Let's start with this group. Can you define S briefly for me? Come on, come on. Oh, okay, Sage Math, I'm dragging it. A minute. Just putting that off screen and just installing this, but I think I'm not going to use it. Cool. All right, now let's define. Now let's define D. What's going on now? Verifying Sage Math. Anyway, so D, yeah, okay, cool. So we've got D. Now we do the following. Now we talk about like, now let's define, wait, open. Yes, I trust the stuff from the internet. Allow. Command line, terminal app. Yeah. Launch. Allow. Allow. All right. Okay, we'll get to this in a second. We'll try that in a second. Let me just try to do these. So the point here is now I want to do so help me define the action of C3. Okay, so define C3. Now define C3. I'm kind of like, I'm basically building the context, right? Maybe that is what's gonna make it. Define C3, and now get me the only non-trivial action from C3 to, was it D? Yes, to D, right? Right. On D. So, it's doing the math for me. I mean, that's kind of what matters, right? So tools, fuck tools. I mean, tools are just hard-coded things, right? Let's see if it finds it. State financial homomorphisms. On to A3. Okay, so it's found these. Now I'm gonna ask it, can you, okay, for interaction, so you have these. Can you summarize all the definitions we've made so far in a brief, high-level bullet points list? Including the all right, let's do a bit of a summary. Now the next step is, so we now have S, we have D, we have the action of C3 on D, and now we're gonna calculate D R times S using an action induced by that action. Summary: S, D, C3, non-trivial action C3 on D. Great. Now let's define G. G is defined like this. And you will need an action in order to fully define G. So please induce the action from the one we just derived. Let's see. Okay, here is where so far it's kind of now taken the path of at least thinking a little more. I don't know if I want to go the quick action way. Do I risk it? Do I risk it? Okay. Just give me a second, okay? I'll be back in a second. I'll be back in a second. Nie mogę teraz, przepraszam. Shut the fuck up. Shut. Cool guys. All right. It's actually thinking. Okay. It is mentioned it's actually. I'm curious how it's going to get that induction thing, that inducing thing, because this is also where I'm a little more lost. Like here, the non-trivial action of C3 on D2 is defined by a homomorphism C3 to the automorphism D. So basically, generator A maps to a 3-cycle in S3 acting on the only non-trivial action. The action essentially just helps you define how then the product is built, right? So this is basically the action is that map is just say like this element is transformed this map to this one, this map to this one, this map to this one, this map to this one. Yeah. I'm not so sure how well it's gonna do. That's the thing, right? Come on. I believe in you. Again, the point is, I'm trying to figure out how to use AI as a tool, really, right? While it's thinking, let's just talk about these a little bit. I'm trying to figure out how to use AI as a tool for two main reasons. One is it's a great tool, right? Like if I'm trying to solve a problem, I want to understand the problem, obviously, right? Because if I just dump these into the AI, I mean, that's one thing. But it's not just, I mean, there's no really reason beyond me wanting to learn that, right? So I think it just makes sense. Also because the point is, I mean, what is learning, right? I mean, there's this thing here. I saw this. I stumbled upon this yesterday. On X. Oh, I think I had this here. Oh boy, yeah, the oh boy thing. So I stumbled upon these yesterday, which is very interesting. The thing is, so it's also just AI powered learning platform. So I guess that's kind of like a version of like the ultra personalized course, right? And I even tried, what I did is I kind of went in and just copy pasted the exercise. I mean, we can even do it now. Let's copy paste the exercise because I have 2 courses left. And I'm just, so build me a course that helps me understand all concepts I need in order to solve the following problem. I mean, I didn't prompt it like that, but let's prompt it like that and see what happens. Okay. So what I did that it was doing yesterday, what I saw that it was doing yesterday is like it's building you like a bunch of resources, like a podcast version, a sort of lecture type of format, notes, flashcards, whatever it is, to kind of have that like 360 approach to learning, which is actually very, very cool. So this course does into the semi-direct products of groups, a fundamental concept in group theory that generalizes direct product by comparing non-trivial actions. I don't know, it seems like it only captured that semi-product stuff and it didn't really capture the block stuff, but okay, it's for the structure of standard products in group theory. So it really kind of created something only for semi. I did copy the whole thing, right? Yeah, I did copy the whole thing. Let me see. Did it? Oh, don't fucking search colors. I mean, it's searching in Math Exchange. Maybe that is. I have no idea what it's gonna come up with. Okay, so action induction. I don't like that. I don't like these. I don't like these. I don't like these. Maybe I need to explore more what this induce here means. You know? Action induction. Does action induction mean something? In group theory, can you induce an action from another action? Well, maybe I'll ask you. I'll ask Rex. Hey Rex. Hey Rex. In group theory, can an action induce an action from another action? No. So can you in group theory induce an action from another action?
Sure, yeah. Like if a group G acts on X and X acts on Y, you can compose G and G sends Y to where X takes it, then G flips X. Boom. Induced action on Y. Works tidy.
Can you say that again?
Yeah, like suppose G acts on X and X itself acts on Y. Then for any G and G and Y and Y, G dot Y is defined as first let X be wherever Y lives. G moves X to G dot X, and then G dot X acts on Y. Same effect, but now G acts on Y directly. Makes orbits nicer to compute.
So inducing an action means that you're basically composing two actions?
Exactly. Like stacking Lego. If G moves stuff in X and X shoves around Y, glue 'em, so G just moves Y directly. Not the same as group induction. That's for reps. But yeah, it's composition with a twist. You're letting G ride on X's influence. Weird how induced gets reused, right?
I'm struggling with one thing. So I'm trying to solve a problem where I'm asked, like, you have a group S and a group D, okay? They're just like, don't ignore the definitions. You have a group S and a group D. Now you're calculating a group G as a semi-product from D on S, D R times S. And then it's telling me that the action of S on D is induced by the only non-trivial action of C3 on D. I think it's because C3 somehow is a subgroup of S. I'm not so sure. But it's basically, does induction make sense in that context where you have an action that is defined in a from a subgroup towards D, for example, and then you're asked about inducing an action from like a wider group towards the same D?
So, drop the mystery. C3 is probably a subgroup of S, right? And since D is, what, cyclic? Whatever. Assume C3 already acts on D. Say, cycling 3 elements. Now, S contains C3, so that action extends to S naturally. Any S in S that sits outside C3 just leaves D fixed or conjugates the C3 bit, whatever keeps the semi-direct product law happy. That's induction. You take the tiny action.
Okay. Wait a second. I'll be back in a second. Okay, thanks. Then I need to correct that. That makes more sense. Can I stop it? Okay, stop. Let me add these. So great. Now let's define G. G is defined like these, and you'll need an action in order to fully define G. This action is essentially the action, the action is actually, it's essentially the action we've defined above because C3 is a subgroup of S. So essentially, for the elements that belong to S but not C3, the action just stays like the identity. What I mean is that we simply want to extend the action we've just derived. That might actually do the trick, because I think it's giving less room for interpretation of what induction means for grok. Don't think that much. Give it a go with just the thinking. Extend the action to S. Let's extend the action to S. That's awesome, man. Define the semi-dark product. The action specifics. Okay, I think we might have it. Formal definition of G. Generators, action relations. Okay, that's interesting. It actually built a text. Why did it do that? Artifact group presentation. Summary of G. We got G, boys. Okay, so we got G. We have an order, we have a structure, we have an action, and we have properties. Okay, I think this might have been the best. This is my best shot at these, I think, so far. So now let's try to do the following. So now we're talking about like a large enough. Okay, so now we're looking for, great. Now we are looking for a field K large enough to study or to build representations of G of this field. This field has char 2. Can we work with a specific example of such field? Can you build a specific field that fulfills these? The thing is, I think LLMs might be great for like math, like to just like kill math software, because I think math software suffers from the fact that it's just extremely abstract to build representations and do calculations and computations. Because a lot is just kind of talking through these, to be honest, not gonna lie. I think it's just gonna be, you know. So the question was finding a field K. So chart 2 divides G, making it modular representation theory. Okay. Why D? G may not have elements of order 6, given D has order 2 elements and S has order 3. Do I want the quick answer? No, what link copy? I didn't copy the link. I want to copy the text. Just go for it. I'm impatient, but I think it's doing better when it doesn't think that much. Okay, so it seems like we're gonna go with field F4. A larger field. Minimal field characteristic 2 with third root of unity may not be sufficient. Final answer. Field F4. Let's try to compute and count how many reducible reps we can find. Modular case. Let's see. Okay, let's give it a chance with thinking. Although, if I see that it's going too crazy, I'm going to stop it and go with a quick answer. Got reps and number 2. Using code. I wonder what code it's going to use. SymPy, okay, which could help. Okay, give it a try, bro. Why not? In the meantime, I'm gonna keep where was I? Here. So the cool thing about these is that it's completely tailored to your problem, right? Or to whatever you ask it that you want to learn. And then you have key takeaways, which is nice. So you have like, it's more like bite size. So semi-direct product definition, normal subgroup in action, properties in order, Schur-Zassenhaus theorem. This theorem guarantees conditions under which a finite group can be decomposed as a semi-direct product of its subgroups. Subgroup. Okay, group action, automorphisms, constructing a semi-direct product. It actually gives you like the stuff that I've really been discovering with code execution. It actually has executed code. That's actually cool. That is actually cool. If it gets 5, if it gets the answer, it's crazy then. Yeah. I still would like to learn more about the field thing. How has it approached that? Think about these, right? So why would you need a large enough field? Because you can of course have small fields where then just you don't have so many representations of that G. That kind of makes sense intuitively if you think about it. There must be a way to reason about these where you reason it a bit more intuitively. But okay, let's go back at these. So examples, dihedral groups, holomorph and reth products, pure mathematics applications. So you've got takeaways, you've got a podcast episode.
So you know how sometimes you can take two things that seem completely separate, and when you mash them together, they make something way more interesting?
Like peanut butter and jelly, or, group theory and more group theory.
Exactly. But specifically today, we're not just mashing them. We're talking about the semi-direct product, which is like a direct product, but with a twist, a really important twist.
Ooh, a twist. Is this where one group decides to act on the other, like making itself at home and changing things up?
Yeah, imagine two Lego sets. One set is the normal subgroup based on N, it has its own bricks and structure. The other set is H, the complement. In a direct product, you just stack the sets side by side. In a semi-direct product, H sneaks in and rotates some of N's bricks every time it attaches. The result can look completely different.
Nice. So let's ground that. What are the exact ingredients we need for this Lego trick to work?
First, we need a normal subgroup in N. That's the set that stays put under conjugation. That's a second on W. A subgroup H whose size multiplies with N to give the whole group's size. Third, a homomorphism F from H into A, and that's the rule book telling H how to rearrange N when they meet.
Let me ask the obvious question. Why does N have to be normal? Can we do this without that property?
If N wasn't normal, conjugating by elements of the big group could move N outside itself. Then the neat pairing, NH, won't behave like a subgroup copy of N sitting inside the bigger group. Normality guarantees N is a stable internal piece that H can act on via automorphisms.
Okay, so that homomorphism, sif H, odd N, what's the intuition there? How should I picture an automorphism in this context?
Think of automorphisms as the symmetry-preserving shuffles of N, rearrangements that keep the group structure.
It's not perfect, but it's actually very good, because I think the podcast format where one of the hosts is asking questions to the other, it's a bit like an internal dialogue in your head, right? And that's kind of, it's like, okay, so why this and why that, right? Like, which are questions that you should be asking actually yourself. What does that button do? I don't want to click it. Wait a second. Then we have a deep dive, which is a read. Okay, so that's then more technical. There's some visuals. This is where algebra comes in. Should I make it? Okay, so arithmetic hides something. It looks a little messy in terms of some of these notes here. Rotation and reflection symmetry is a regular pentagon. Yeah. Okay, so that's a deep dive. Then we have a lecture recording.
Picture this. You have two neat, well-behaved abelian groups sitting on a table. They commute, they get along fine, they're predictable. Now hand one of them a single non-trivial automorphism and watch the conversation turn into something far more interesting. What happens when structure meets motion? When symmetry acts on symmetry? That's the heartbeat of today's exploration. We begin by holding tightly to the basic anatomy. Suppose N and H are groups. I'll write elements of N as N, and elements of H as H. The semi-direct product is a way to fuse N and H into a larger group so that N sits inside as a normal subgroup, H sits inside as a subgroup, and the way H moves N is encoded by a homomorphism from H into alt N. That homomorphism, call it FH alt N.
Wait, actually, that gives me an interesting mental picture. So it's like, because it says the way H moves N is encoded by homomorphism. So it's like you're trying to, it's like these, right? I guess canvas, maybe. I'm just so you have, let's say you have H and then you have S or whatever, right? And so when you're doing the product, you're kind of doing something where H is a subgroup of it and S is a subgroup of it. But there's been kind of a movement, I guess, maybe. That's an interesting idea. In this movement of S that places it somewhere in a specific spot in that bigger group is defined by that homomorphism. That's an interesting, I don't know, maybe I'm wrong, but like that gave me an interesting image. Okay, what is it doing here? That 3 class 11 being too regular. Okay, it's doing something. Report is anything. Okay, it's cooking. Let's let it cook a little longer.
Structural instruction. Each HH tells you how to rearrange elements of N. Concretely, the set is the Cartesian product nxh with multiplication defined by n1 h1 n2 h2 x n1 f h1 n2 h1 for e b out to e and
I mean, it's hard. The problem with these is that it's hard for math problems because, like, reading these is like they're not great at these. But I guess that's just gonna be soon fixed. It's a general thing where I guess here they suffer from some like notation creep or stuff that kind of comes from maybe LaTeX or like other writing conventions, and you can't just read them out loud. Like, I don't think these voice models know how to read those things out loud. I mean, even Grok does a poor job with these. 11? No. We know it's 5. We know it's 5. We know it's 5, and it's not 11. So I actually didn't get it. Maybe we should do these. So let's actually. Can I try? Ignore the 11 result for now. Let's build examples one by one. Let's build concrete examples one by one. Examples of EREBs. I think that could actually help it. Group G, group K, field K. One-dimensional ones and the simplest, yeah, exactly. Okay, I like it that it's going with the easy ways. Example 1, trivial representations. I don't want text. Okay, it's actually writing. High dimensional representations. All are irreducible. Total. Okay, so that's just 1, I guess. Choices? No, 9 choices? Makes no sense. So let's stay with the 1D ones. And can you walk me again around how you count them? List them if need be. I feel I'm almost there, you know, that's the thing. I feel I'm almost there to get it to the right answer. At this point, I'm not able to, I mean, I'm definitely not able to control. That is, so it actually finds 9 choices, hence irreducible. That's already more than 5. So Can you check if any of these 9 are equivalent? Would you really count them as separate, hence separate blocks? Check for equivalences. All pairs are distinct. Large enough. I mean, large enough field with characteristic 2. How many blocks does cage have? Large enough. The problem is that it's large enough. Like, is there a smaller field? Okay, so is there, so can we repeat these but over F2 instead of F4? Because that's the problem, right? So the problem is it's that we're not we're given a very vague, like, it's like, let K be a large enough field, right? So we just have to find a large enough field to do that. It doesn't mean that that's the max number of blocks that you could find given any K. You know what I mean? You're not proving any. That's kind of a bigger, that's an important aspect of these. Okay, so it's doing F2. I hope that I haven't polluted it too much with all my other now, context. This probably like pollutes the context, right? No, don't compare with F4 blocks. Okay, 1, I like that. F2. Let's take final answer. So F2 is exactly 1 irreducible representation. I like that. I like that. It's less than 5. Let's stick to F2 for now and ignore F4. Can we calculate the IREPs of G over F2 for higher dimensions, higher than 1 dimension? Because F2 maybe is an auth. Then maybe you need to understand why F2 is an auth. I mean, there's a lot that I could dig into here. That's the problem. That on one side, I just want to solve I just want to be able to manage to solve the problem. I mean, at least I've understood now a nuance that I hadn't captured before, which is like, that's an important large enough. It's an important restriction here. We want to have a large enough field so that it's not too small that there's just one representation, but it's not too big that there's just like infinite representations. So we just want to find a large enough field. I think that's what it means, right? Let's see what it does. And I might have to stop here, but I'm on a very, very good track, I think. With order 3, let's see if it figures it out in like a couple minutes, and then we'll come to the next thing, and then I'll come back to this. I'll come back to this tomorrow, I guess. In the meantime, let me check one thing. I'll just for a second stop the camera in the mic. I'll be back in a second. Okay, sorry, I was just checking something from the system. Quick answer. Let's go quick answer. Let's go quick answer. Let's go quick answer. Quick answer is doing better than I thought, man. Way better than I thought. Yeah. While it's thinking. That was an interesting take. I mean, that's an interesting concept, really. You have a lecture recording, then we have studies. You have frequently asked questions: how does semi-direct product differ from direct product? Or group actions and how they semi-products. A group action form way to describe how elements of group A symmetries. I mean, you know, it's interesting because it gives you questions to be non-unique. Semi-dark products. Then we have flashcards and word quest and quizzes, true or false. In a semi-dark product G, and the subgroup N is always normal. In G, false. Oh, true. I thought I thought age was normal. Next. The order of the semi-dark product. Is it the product order is true? Yeah, right. If the group action defining the semi-dark product is trivial, then G is dark E. True. That's true. I've learned that with Grok. The dihedral, I have no idea what that is. Anyway, has it finished thinking? Did I kill it? Ooh, switching to F4. What? Gee. Really? Okay, anyway, I'll stop here. We're there somehow. I need to. The problem is I quickly get that context polluted with questions. So it complains that F2 is too. No, 2D attempt. Keep trying. F2, please. Don't give up. You are a great group theorist. Thank you. Let's keep thinking at this. Then maybe just go dimensions 3. I don't know. Go to the higher dimension. It doesn't have to be dimension 2. Come on, let's go. Let's go. If you tell it nice things, then it actually goes for it. It's cranking the math for us. That's good. Isn't sufficient. Yeah, let's great. Try 3-dimensional representation. That's good. That was a good point. No, don't switch to F4. F4 not good. F4 not good. Try higher dimensions. In F2. What about 4 dimensions? Come on. I think I'll have to sort of clean some of it up. But that's using it as a tool like this instead of using a tool makes more sense, kind of. But at least I've discovered one thing here, which is this large enough is important in the problem. This is important in the problem. Quick answer. Let's go. You can do this. You can do this quick. You can do the quick answer. I know you can. What are the third roots of unity? But f4 gives us 11, and we don't want that. I know that is not what we want. Does f3 make sense? Can we try f3? Or does it make sense? Or it doesn't make sense? Ah, has characteristic 3. Let's try stop. Let's find first a list of candidate fields of characteristic 2 that are small but large enough to study reps of G. Let's start here. Let's make a list and then let's walk from there, because it feels like f2 is too small, f4 is too big, and we want something that is large enough. And quick answer. I don't know if quick answer is always a good thing to do. It's yeah, it seems like it should be in this case. f2, f4, f8, and f16. Algebraic closure of f2 contains all roots of unity. Really? Not so sure we need to stick to the third roots. Okay, I'm gonna stop here. But I think I'm onto something here. I stop. It's just kind of, I'm getting a lot too much into the weeds, I think, at the moment. As in, like, it's the problem here is that I can't follow in detail the reasoning too much because I'm lacking the knowledge, right? So maybe I should step back for a second and dive into how to choose a field to study the reps, the E-reps of G. Maybe that's the question that we have to ask ourselves. How to pick a field to study the E-reps of G? Because I think it's fairly easy to construct G, and we have something here in this chat. So we'll look at it in the next session. Bye-bye.